Okay, hello everyone. This is the second Agda problem solving session of the HoTTEST summer school. And I'd like to start off by asking if anyone has any questions about the lecture.
I'm not sure if this is a question about the lecture or something that'd be more appropriate for the exercise discussion, but I find myself, as someone with a functional programming background, hearing that not all values of the identity type are refl was something that I could sort of hold in my head in the mathematical interpretation, but seeing the definition of the identity type in Agda having a single constructor, I'm finding it really difficult to understand how a term of that type, if it terminates, would reduce to anything other than an instance of that constructor. And it's making me wonder whether there's something I just profoundly don't understand about Agda, or whether we're going to add additional constructors to that type in the future once we introduce more axioms, or whether I'm just not as smart as I thought I was, or how that could be possible.
So that's an excellent question. In regular Agda, well, I can give you a very easy example of terms in the identity type that are not reflexivity. So for example, I could postulate that I could have a variable in the context. So suppose that P is a proof of true equals false. Right? P is a variable. Or I could have a function that postulates proof of true equals false. And so variables don't have to normalize. Variables are just variables, right? They're unknowns. So you can have an unknown proof. That's one way that you can have a proof that's not definitionally reflexivity. Another way is, suppose the unknowns aren't proofs. Suppose the unknowns are natural numbers, and you have a proof that's A plus B equals B plus A, the commutativity of addition. Well, you'd imagine that that proof, it has to be a proof by induction, because the functions are defined by recursion. So the proof term is going to be some big thing that's defined inductively. But it can't be reflexivity because you actually have to prove something. There is a result to be proven. So that's another way. However, you have this meta theorem in Martin law of type theory that if you have a proof that A equals B, and this is in the closed context, then that has to be definitionally reflexivity. But that's only because the theory doesn't allow for more things. So what happens really is, even in cubical type theory, where you have higher inductives, where you actually have non-reflexivity proofs, you can still work with the Martin law of type with one constructor. But the main catch is, the reason there can be multiple things is because there are two endpoints. So let's see, let's go to prelude and let's go to identity types. What happens is that within this constructor, X appears twice, right? So what happens if you have an equality of X with Y, right? And then suppose what you do is you transport it around the identity type from X to Z, and Z goes from, so let's say, X to Y, right? And then let's say Y equals X, but let's say that path is a non-trivial path. Then you have this transported term. And what happened is one of the constructors stayed fixed, but the other one went around in a circle. And now that transport, it doesn't go away. So the key is that you have these 2 points, and those 2 points have to be the same, except for the fact that you can transport moving only one of the 2 endpoints. And then you're sort of keeping an endpoint fixed, and then you're pulling something across.
Yeah, so I think in the mathematical interpretation, I've wrapped my head around the idea that induction on the identity type lets you form proofs of X equal Y, where X and Y are different things. And I think that explains, I think that's a rewording of what you just said, unless I'm missing something important. I guess
Well,
this is
the key thing about the induction principle is that the induction principle is basically for this type where, well, in this case, where both endpoints are free, but you can fix one of the endpoints. So it's induction principle, not about equalities at a point, but about essentially the path space. So in topology, the intuition is that imagine that you have some space, right? And imagine that you have the space of all paths starting from a point and going somewhere, right? Well, then I can give you a uniform way to turn every single point in this space to map it back to the starting reflexivity path at point. So for a given path, you contract it with a time parameter t, and that's a uniform description that applies to every single path, right?
Yep.
So this is the topological result that the path space is contractible. But what happens is that now suppose that you're working in the space of loops at a point, right? Well, now the second endpoint is fixed, and now you might have a hole in the space and the loop might go around that hole. And now you can't contract it because you can't pull it back along the path because the endpoint has to be fixed. So the induction principle does not apply for proofs of x equals x. And that's why you can't reduce a proof that x equals x to reflexivity. If
Yeah.
that's your constructor.
So I won't claim to understand that perfectly well at this point, but I think I see it a little bit. But my question is more about Agda.
Yeah.
From your initial comments, it sounded like it looks like there's an additional language construct in Agda called postulate, which lets you say, regardless of what constructors we have available for this type, let's add a new one in an ad hoc way.
Yeah, exactly.
Okay, so I think that answers my question, is that we can postulate additional instances of a type in Agda, even if it looks like it has a closed set of constructors. Nothing ever really has a closed set of constructors in Agda.
Right, and it's not even about postulates. You can also just hypothesize something as part of the ingredients of a function. So your function hypothesizes a proof. It's in your context there. It's a variable. It doesn't reduce.
So, sure, but in order to use that function, you'd need to provide it with a term of that type at some point, right?
Yeah, well, you can think of a postulate as being roughly the same thing. But in cubical Agda, we don't actually have to postulate things. There are actually higher constructors that you can build into the definition of a type.
But you would add it to the definition of the identity type in that case.
No, you wouldn't actually. You could use the Martin-Loff identity type. That's the beautiful thing. I can't explain this right now because this will take a very long time to develop, but no, the Martin-Loff identity type works perfectly well in cubical Agda.
Cool. Do you have a quick link to something that I could read, maybe, or keyword I could search?
It's going to be explained later on, I guess, if you just continue with the course. So it's just going to be like basically learn HoTTEST is going to be the answer.
Good enough for me. Thanks for your time.
Yeah, no worries. Anyone else?
Well, so I was just thinking, I don't have functional programming background, and he mentioned they mentioned constructors and closed set of constructors, but even just in the lecture, they said just because you give, the intro rules, that doesn't mean that that's all the possible terms of a type that you're defining. You're not specifying, right? I mean, is that true? Like whenever you say what the canonical terms are, you're not saying those are the only terms.
The thing is that there's an induction principle, and the induction principle in most cases, you can just naively think about it as saying that if you have a term, then it has to be of a certain form as one of those constructors.
Yes.
The problem is that in the identity type, it's a very weird case where you have it's an index data type and an index appears twice. And that causes all of the issue because the induction principle doesn't apply to loops. It only applies to free paths where one of the endpoints can vary.
Okay. So induction is, equality or identity is special in that sense because, like, even though the way we defined, pairs in the HOT lecture, there's not a definitional ADA rule, right? I know that we maybe have it in Agda, but I know in the lectures it was a propositional equality that all all elements of the product are pairs.
Yeah, well, that depends on if you define it as a record or as an inductive type. But whether it's an
Right.
Ada rule or not, it sort of doesn't matter if it's definitional, because if it's not
Or
definitional,
not.
then you just do induction and you get it.
Right. So I guess what my point was, though, is like the point of HOT is not to make elements that aren't pairs, but we will be making elements that aren't reflexivity. Like that's where
Yes.
identity is different than products in that sense, even though they
Yes.
both might not have judgmental Ada rules in the way that it's defined in the lecture. Okay.
That's right. Any other questions? And then we can start some problems. But this is a good discussion, because the identity path, it's very weird to understand. But I think that before you can even ask yourself a question such as, how can there be a loop constructor in a circle? You have to understand that in the presence of contexts, which don't even necessarily have to postulate equalities, they can just postulate natural numbers. And then if you have a proof that for all natural numbers n and m, n plus m equals m plus n, that isn't going to be reflexivity, because that's an actual math theorem that requires an actual proof. And your element of your identity type is an actual sophisticated proof with a lot of detail, right? So I showed you last time in proofs the normalization, which I wouldn't get in Agda because it wouldn't be written in terms of eliminators. But yeah, so that's the important first thing to understand about equality. And then you have to ask yourself these other questions about equality, and they'll come up in due course. Anyway, okay, let's get started with some problems. So here are just some basic problems on pattern matching. What we have here is we have some function f, right? And it takes two arguments, and we want to produce a function on pairs. So what we do is we take the pair argument, we split it, and we get it as being a pair of things. They come from A and B, so let's call them A and B. Well, then how do I get an element of X? So let's look at our context for a second. I have A and B, and I have a function f from A to B, from A to B to X. So how do I get an element of X? What am I going to use?
F of A of B.
Yeah. And then, for example, if you didn't want to do that directly, you could just do F, and then you could refine. And then you'd see here that you need an element of A and then an element of B. And this is just going in the other direction. So if we have a function f and now we have A and B, we're now going to package those as A comma B. Okay, then there's a bunch of things in working with sums and implication and negation. We might as well jump to the slightly more tricky exercise. So what is negation? Negation is, by definition, implies identity. So not A means A implies, A implies a contradiction, the empty type. And that's a main thing in classical logic. Well, let's say we're working with something like a triple negation elimination. So what this says is that if you assume not A, then you can conclude not A. And so I'm going to assume a proof of not A, and I'm going to call this neg A. And then I'm trying to prove not A, right? But what is not A? So here it's telling me I'm trying to prove not A, but I can normalize that. I can press CU, comma, and then it'll normalize the goal, and it's A implies contradiction. So I can then assume a proof of A, right? So now I have a proof of not A and a proof of A, and I want to prove contradiction. So first off, in my context, there's only one thing that lets me prove contradiction, and what is that?
Not A. There's an
Yeah,
element.
so
Not A.
That's going to give us some way of proving contradiction, but then we need something. What do we need? So let's just refine it. We need a proof of not A, right? And that's a proof of not A implies 0. Well, that means that we can abstract over a proof of not A, right? So now I also have a proof of not A. Did that step make sense to everyone? Right. So to see what the type and the goal is, you press CCC comma. So CCC comma. And then if you want to normalize things, you also add CU in front of it. So CU CCC comma, or just CCC comma. Right. So here we're trying to prove contradiction. And what do we have in our context? What are the last two arguments? So we have not A and we have A. How do we use those to prove contradiction?
Just give it A.
Give not A, right? That's contradiction.
Yes.
Cool. So we've proven that it's not the case that we have double negation elimination. But if the type which we're trying to double negation eliminate is not of something, then it works. So the law of excluded middle holds for types of the form not A at the very least.
So just
Well,
a quick
double
question.
negation elimination, not them. Go ahead.
Right. Just a quick question. Why, whenever we're defining double and then triple negation, the double negation has an underscore, but the triple negation doesn't?
That's absolutely accidental.
Oh, okay. Okay. I just thought that was like a whatever it's called, a postfix or whatever.
So this is going to
Operation.
be it is going to be a fixity operation, and it does change the way that the parser works.
Okay.
So for
So
example,
the underscore didn't really break anything, but it's not necessary.
yes.
Okay.
So I could show you. Let's say I put an underscore here. Let's say I didn't put an underscore here. I think that these brackets are superfluous, and they still would be if we did that. So it changes the order that ways or if things are parsed is my reply, and I'm not going to get into specifically how.
Okay, but we don't need the underscore as long as we're
No, we don't.
careful with the brackets.
Yeah. Okay, let's prove two more things about iterated negations. So this operation of double negation, the claim is that we can apply it to maps. So if we have a function from A to B, we get a function from the double negation of A to the double negation of B. So what are we going to assume? We're going to assume a function f, and we're going to assume a proof of not A. Well, I could just look at what the context is, so not A. And I'm trying to prove not B. And what is not B? Not B is not B. So then I could take a proof of neg B. And I'm trying to prove contradiction. So let's see. I have okay, how so we have two functions that are going to allow us to produce contradiction, right? If I use not B, then I'm going to have to produce an element of B. I have an element of not A, but I can't produce an element of A out of that. So that doesn't look like it's going to go somewhere. So I should probably use not A instead, right? And then if I use not A, I need to produce a proof of not A. But I know, so what is the proof of not A? I can abstract over A. Is everyone following? Questions? Cool. So now I'm trying to prove contradiction. I have not B, I have A, and what else do I have that's going to be really relevant?
You've got an F.
Yeah, so F lets me turn the A into a B, and then what?
And then not B will turn a B into contradiction.
Yeah. Bam. So proof assistance really helps you with this. If you were doing this proof on paper, it would be a bit more difficult. Let's see here. So we have a function F from A to not B, and then we have neg A. And what are we trying to produce? We're trying to produce a proof of neg B, which is in particular neg B implies contradiction. And all of the arguments are named appropriately. And we're now trying to prove contradiction. So what are we going to use? Well, F is sort of a hard way to prove contradiction. We need to pull an element of A out of thin air, and we can't pull it from not A. So that doesn't seem very useful. On the other hand, what about something like not B? Well, we need to pull an element of B out of thin air. So let's try using not A again. And in particular, we now need to prove not A. So we can get an element of A, which is useful. It's going to let us proceed. So if I have an element of A, then I can feed that into F, right? And that's an element of not B, right? But what do I have a proof of as well?
Not B.
Yep. And so that gives me contradiction. And then these things have meanings in category theory. The functor one is, it applies to morphisms as well, functions. And then this one is a bit more abstract. Okay, let's work on this extended series of exercises that show that true does not equal to false in a provable way. So the first thing that we're going to do is we're going to define a type family over Booleans, so that true is inhabited and so that false is not inhabited. And we have a canonical inhabited type. Which type is that?
0 or empty.
That's the uninhabited one.
One unit.
Unit. Okay, so true is units and false is 0. This is going to be a type family over Boolean. So for every Boolean, we have a type. For true, we have the unit. For false, we have contradiction. Now, I'm going to claim that these two types imply each other if and only if the Booleans are identical. And so if you're wondering what this is, then I'm just going to go to meta dots, and you can see here that it's defined as by implication. So it's the product of A implies B and B implies A. Now, how am I going to prove this? So how am I going to use this equality? How do I use an equality?
Path induction.
It's in path induction, yeah.
Yeah, so I can notice that basically the key is that the endpoints of this path are free, right? So for example, let's suppose instead that I had a proposition like this to illustrate what I was talking about at the beginning of the lecture. So we're using without K. So I now have an equality between B and B, right? Let's say I try to use path induction on this P. It would complain. See, I can't do path induction on it if both endpoints are the same. The key is that there have to be free endpoints. Both of these have to be free. But if we have B and B prime, then I am able to do this path induction. So that's an important thing to understand about the induction principle on paths. Did that make sense? So let's look at what the goal becomes. The goal becomes showing that bool as type B is the same, implies bool as type B. Well, let's just refine this because that's actually a product and we need to prove two things. Here we need to prove that this implies this. What's a good proof that something implies itself?
Refl.
Well, that would be an equality where we want a function.
Identity.
Yeah. And here we just want the same thing. So this lemma was dispensed of with a path induction. Okay, I'm moving these things so that I can actually see. There I have multiple Zoom windows open and it's difficult to navigate with Agda at the same time. So let's see how this implies that true does not equal to false. So let's start off with a proof that true equals false, right? And we want to show that there's a contradiction. Well, what could we do? We have this thing. What are we going to apply it to?
P.
Yeah,
Or wait.
but in particular, we also need to put in two more arguments, and those are true and false.
Right. We got to give it the Boolean.
So what does that give us? That gives us that there's a by implication between true tautology and contradiction. The unit type is also known as tautology. But that's a problem because tautology implying contradiction isn't good, right? So if I look at sort of if I normalize what this is, well, unfortunately, it's not very useful because there's an implicit. But it's the first argument is that one implies zero and the other one is that zero implies one. So we're going to take the first thing, right? Because that's the problematic one. That's tautology implies contradiction. And so to access fields of a pair, we're going to use the first projection. What does that give us? It gives us a proof that tautology implies contradiction. So we can get contradiction if we have a proof of tautology. Well, I guess I can just look at this
Star.
and I can look at what its constructor is. And it's a star. Yeah, exactly. So I now have a proof of contradiction. Any questions?
I'm sorry if I'm beating a dead horse here, but the example that you gave of why you wouldn't be able to use pattern matching on refl if you wrote bool equivalent to, or bool equivalence characterization, I guess that's what this is, with b equivalent to itself. You could implement that by passing B twice and P once to the actual Boole equivalency characterization function, right? Which means that you're taking the path that you were given, whatever it is, whether it's refl or not, and you're passing it as a parameter to the original implementation that you have there. And that original implementation only expects the path that it receives to be a refl. So how does
Right,
that not
but
imply
however, here's the key thing. Let's imagine that you have let's imagine that we put the Booleans here instead. No, well, the thing is that here I have the identity and the identity, right? If you have not the Booleans, but you have more interesting types with more interesting structure, you could actually make it be the case that if you pass it a non-identity path, these functions no longer become identities. You could make it such that, for example, if it's a function from the Booleans to the Booleans, it switches both Booleans. For that to happen, we wouldn't be working with equality types on bools. We'd be working with something more interesting. But I can give you an example. Suppose you have a circle. What is a circle? Okay, it's just a circle. And at every point on the circle, I'm going to define a 2-point set. So at the base point of the circle, it's going to be the Booleans. And the way that a cubical Agda works is that I need to specify how going around the circle acts on this. And it's going to act using knots. So it's going to flip the points. Then basically here, you could do something like this, but you could do pattern matching. But what happens when you pass it the loop instead is that it would actually turn these identity functions into transpositions. That's possible. That happens.
So, so let me try that. Like, are you saying that basically, it sounds like you're saying that the pattern matching in Agda is not saying these are the only things that this function can accept. Instead, it's saying this is like some kind of action that is generated by these base elements of this type. And so you can give it more complex elements, and the behavior is completely determined by those generators, but it's not as straightforward as pattern matching in other languages where the generators are all you can give it.
And the reason is that topologically, remember, the loop space is not contractible, but the path space is contractible. The contractibility of the path space means that to define a function on the path space, you only need to define it on the reflexivity point because there's no other information. But then if you evaluate it on a non-trivial loop, then you get some interesting action happening.
Cool. This is wild. Thanks.
So this will, again, become clear later on when we talk about higher inductive types and transport and how transport works and transporting cubical Agda as well. Okay, now we'd like to prove the opposite characterization. That's if the types families over two Booleans imply each other, then the Booleans have to equal. Well, okay, so we have by implication. So we have Booleans B and B prime. And then we have a by implication. And that's going to be a pair of functions f and g. Now, there's no path to do induction on, and we really can't do induction on functions. So what are we going to do induction on?
Booleans or
yeah. So let's split it up entirely. 4 cases, right? So if we have true and true, we're trying to prove that true equals true. And that's just refl. And similarly, sorry, it's refl true because both equal true. False and false, we're trying to prove false equals false. Why is false equals false? Because both equal false. Whereas these cases, what happens is that we have assumed these by implications. And these by implications are a bit of a problem, right? So we have, for example, the implication tautology implies contradiction. So that gives us contradiction. How do I get contradiction? I apply F2 up.
Let's see. True's first, so apply F to true.
F takes a unit, an element of the unit type.
Oh,
So this is a by implication over the type families over the Booleans.
So
So
we have
with
to
true, the
star?
type family. Yeah. So star. So that gives me contradiction. But how do I conclude something from contradiction? Well, anything follows from contradiction. Now, how does anything follow from contradiction? Well, typically you use the word absurd. But unfortunately, the names in this class are weird. So let's just look at what the names are. Okay, so it's 0 elim. There's also 0 non-dependent elim. Yes. And so this proves anything. Right? And here
we don't have
also
to
have a
specify
problem.
what A is that we're trying to prove.
So that's going to be the unifier is going to solve that. So here it proves, and if you can see that it proves anything. Now in concretely, it wants to prove true equals false. So it's able to figure out what it should plug in for that eliminator as an implicit argument
Okay.
from the goal.
But we could give it like the curly brackets, true equals false.
Yes.
Okay, cool.
Except for the fact that this is the general dependent eliminator, which is weird because
Right.
so if you use the non-dependent eliminator, then you could do that, and then you could say that you're eliminating at A is the type true equals false.
Right. Okay, cool. I'm cool with
So
Agda
this
being
should-
able to figure it out, though. I just wanted to make sure I understood.
Yeah. But non-dependent eliminator is a long name. In any case. Well, here, what's the problematic? Is which one of is problematic, F or G?
G.
Yeah. Okay, so what this shows is that two Booleans being equivalent is the same as the by implication over the type family, logically, that these two things are logically equivalent. Logical equivalence means by implication. So there is a by implication between these two statements. I could write this. For all Booleans. By the way, the for all here, it's not necessary. You could remove these. For all Booleans, there is in fact a by implication between these two statements. Now, how do I type by implication? Well, I'm going to press CU CX equals, and then it's going to tell me that it's if and only if. That's what I type. So I get this if and only if, and then just to specify how to bind stuff in case it needs any help. And then this is just a pair where the two results are exactly this at B prime and this at B prime. And these parentheses are not actually necessary. Cool. So let's see how we are for time. let's, I guess maybe we can do some of the easy exercises that I skipped, or we can do this thing about decidable equality. Actually, this thing about decidable equality looks more interesting. So let's just analyze this type and try and make sense of what's going on here. So this says has bool decidable FCT. So what this says is that for all families that are decidable. So what is a decidable family? So what's a decidable binary relation? It's a relation by two elements that's just given by, for any two elements, you either get true or false. They're either related or they're not related. So this says that what there is that there's a decidable relation on A such that for any two elements, they're equal if and only if this relation decides as true. So I think I'm going to rewrite this in a different way. That's probably a bit less obscure. So what I'm going to write is that this is going to be a sigma over R, or rather, let's call it sim. And let's make it an infix thing. I can do that. So X and Y, if and only if X is related to Y, is true.
And the colon there in the sigma type is the one we talked about yesterday, the colon 4, to make sure that Agda knows it's not the colon that we use for other types.
Yes, it is. It's a special syntax declaration for sigma types that Martin used. That's not part of the standard library, by the way. So has decidable equality. What is this? Well, is decidable. So you have decidable equality if equality is decidable. What is decidability? It's A or not A. So it's A coproduct, not A, right? So decidable equality means that we can either, for any two elements, we can prove that they're equal or that we can prove that they're not equal. And we'll be able to do one of those. So we'd like to show that if A is a type, then we have a certain by implication. I forgot the type of what I'm proving. So this is a by implication. We can refine it to two separate theorems. The first theorem is that if we have decidable equality, we should actually just split this into two cases. So I'm going to call it case 1 for all types A. Left implies right. Just to avoid having lambdas inside of there. So then we're going to take a proof of this, and then the thing that we're going to try and prove is that this assertion holds. So there's going to be some relation, and then there's a proof that that relation is exactly the same thing as equality. So what do we have? We have as a postulate decidable equality, right? So the relation is going to be something, and I'm going to construct it here with using a where statements, where the relation the identity type uses sim. Of course it does. Why does Martin do these things? Fine. R. So I have X and Y, and I have this proof of decidable equality. So in particular, this tells me that for every two elements, X and Y, I get a decision on whether I have equality or not. And what I can do is I can use a with condition on this. And then here I can say, okay, so the result is going to be, let's say, Z. Oh, and Martin spoke about either saying Z or Z. I am Canadian, so Z is correct. And so we're either going to get a proof of equality or a proof of disequality. So then let's say X and Y are equal. Then what should we say? That the relation is true. And here the relation should be false. So I've now produced a relation. And here I'm supposed to produce a pair of relation and by implication of that relation with equality. And it's an index relation. So I have to type this. And the goal here is to show that X equals Y if and only if X and Y are related, right? Okay, so one of these directions is easier, and one of these directions is a bit more interesting. Let's consider this direction. If the relation is true, then I get X equals Y. Now, what I'm going to do is that I'm going to postulate that the relation is true. And now I can split on what value that actually has. And notice that Agda eliminated one of the cases for me. So Agda was actually nice. However, the problem is that I lost information with this. Now I'm going to just do something absolutely ridiculous that I should not be doing in this problem session. And that's to just quickly go here and open some secret code that I shouldn't be showing you. Scroll to the top of this and use what is called the inspect idiom. Okay. Now, in order to make sort of with statements not useless, I'm also going to do inspect px. Here. Here, rather. And what this is going to give me is something, which is going to be a proof that that did not work as intended. Okay, yes, this is this use of with in Martin's code is not going to go through this time, unfortunately. This is split on pxy where p is what? Oh. Let's just see what the original goal was. Let's split on pxy. Let's do that. That's more interesting. Okay, R is a proof. Okay, let's just ignore that happens. Yes, so the correct thing to do was to in fact split on pxy. And there was an easy way to do that. And here, what we're going to do is we're going to prove the reverse implication. So this is how Agda development usually works. And here we have a free endpoint. So here we can do path detection. And so we're trying to prove x related to x is true, but x related to x is basically contingent on this pxx. So we're going to do the same thing with pxx. And let's see if Agda is smart enough to eliminate the case. Okay, but this is fine. Because in one case, we have that the goal becomes true equals true. And in the other case, the goal becomes false equals true. However, we have a proof that x equals x implies contradiction. And that handles that. Except for the fact that it's not able to defer this. So I'll do the non-dependent eliminator to remove that unsolved meta. And then finally, I'm able to combine both of these into a proof of this. So I need to prove that for all things I have a by implication, that's going to be a pair. And that pair is going to be lemma 1, lemma 2, lemma 1, xy, and lemma 2, xy. And these parentheses are superfluous. And that proves one direction of the by implication for this theorem. So what I did is I did some cleverness with width. And then because this was defined with respect to this width, I was being very silly by doing a width with respect to the relation. But it simplifies only if and only if we use the same width that we use to define this expression. So that covers one of these two cases, and this is actually a pretty tricky exercise. Any questions? That was not the clearest last example, but it did show you how working with Agda usually works, and a bunch of
It also
orders get this.
It also looks a little better than what was given in the solutions. But one thing that I was just sitting here thinking about is I still don't really know what width is or does. I see that it's very useful because you've been fond of it, like to use it. Like it seems powerful, but I don't understand it because we've not seen it in lecture. So what width does? Could you maybe just talk about that? Yeah.
That's P of XY. So like what type does this have? Well, this is going to be either a proof that X equals Y or a proof that X is not equal to Y. And so it's going to be an element of a disjoint union type. Well, I'd like to know, I'd like to give the definition in the case that it's X is equal to Y and in the case that X is not equal to Y.
Okay.
So it lets me split on an arbitrary expression that's not necessarily one of the arguments, right? Because if I have an argument, I can split on it. That's easy. I just case split on it, right?
Right. So it lets us do case splitting
without
an argument. Okay.
Yes, it lets me case split on anything that I can derive as some expression out of arguments and definitions that were previously made.
Okay.
So what you do is you could write X equals Y instead of triple dot, but triple dot also works. And then you do X, and then X, so you put something here and that becomes bound to that expression, and then you can case split on it. In this case, Agda was able to eliminate the in our case, which is nice. Otherwise, I would have had to prove that it's impossible. Let's see what the solution is. I haven't actually downloaded the solution, so I will go to GitHub and I will look at what the solution is. Let me quickly screen share Chrome. So the solutions here are actually potentially shorter than what I have. Because this is already a, no, this is a left to right implication. It uses width. The solutions use width as well.
Yes. Yes, I was aware of that.
Mm. Okay. Well, so hopefully you learned something today. The very last section was not ideal, but we did do a bunch of interesting examples prior to that. Any questions?
Yeah, so just to clarify, I wasn't saying that you were using with without it being defined. I was saying in general, that even the exercise was, and that's why I wanted to know more about it. I didn't. I just wanted to
Right.
clarify.
Yeah. Okay. Sounds good. Let me